Well, hello everyone. I'm happy to join this session today to talk about Kubernetes networking and the scope of platform engineering. So this is called the Platform Engineer's Survival Guide to Kubernetes Networking. And I'm afraid when I was preparing, I realized we could spend like 3 or 4 days on the topic. So this is going to be like essentially Kubernetes networking 101, Kubernetes survival skills, right? So probably, if you're using Kubernetes as I guess probably a lot of you do in the scope of platform engineering, you've deployed your application, everything works. Pods have their IP address, they're able to communicate with each other. Maybe you have layer 7 ingress and so on. But do you want to actually know how this works and understand how to debug it in some way, right? So the idea here will be to go through some basic horror stories and understand why they can happen and what are the roles of the different layers. So Kubernetes networking has a bad reputation. It has a reputation of being complex and being hard to digest, right? It's essentially layer upon layer upon layer to the point where you're wondering what your application, right? There's like a layer 4 load balancer, and then maybe after that, there's some kind of layer 7 ingress, and then kube-proxy does the internal layer 4 load balancer, and then there might be some magic connecting the different services inside the cluster for service mesh, and somewhere in there, there's the application. So my name is Raphael. I'm a senior technical marketing engineer at Isovillain, where I've been working on Cilium, Tetragon, and other products based on eBPF. And in my career, I went from essentially DevOps config management, so doing a lot of CF Engine, Puppet, and then Terraform, and then started orchestrating containers first with Rancher Cattle and then with Kubernetes, and ended up somehow doing this cloud native networking and security thing. So I think I understand a bit of the pain of coming from the sysadmin slash cloud architect slash platform engineering world and having to learn this whole networking stack and how it relates to deploying applications on orchestrators and Kubernetes in particular. I still think DevOps is still an important thing, and I love these little plushies that Dell has been giving around with this platform engineering dragon, or is it a dinosaur? I don't know exactly. Hugging a dev and ops cat and dog. Because obviously cats break things and dog keep things running, right? So with that, the program for today is looking at the different layers in Kubernetes, starting with Kubernetes itself and the networking layers in Kubernetes itself. Then we'll talk about services, layer 4 services. A little bit on DNS. I won't spend too much time on DNS, but what would we do without DNS? Then layer 7 ingress, how to route traffic north-south into the cluster using a layer 7 logic. And then we'll talk about service mesh. And then I'm keeping a little bit just as a reminder, because I won't have time to extend on this, on security and other things. So let's start with Kubernetes itself. I call it the naked cube, right? I don't know if some of you have done like the Kubernetes the hard way guide I did this years ago when Kelsey Hightower put this online, and you learn the hard way that Kubernetes is a complex beast, right? There's a lot of TLS involved, but even Kubernetes itself doesn't have a default networking layer. Essentially, you could implement the basic networking between nodes and between pods the way you want to. Typically, you could decide to have one CIDR assigned to every node and have static routes to route traffic between the nodes. That would pretty much work as long as you can assign the IP addresses to the pods. So instead of having a standard for how networking works and is implemented in Kubernetes, what there is there is a standard interface. And this standard interface is called CNI. So that's the first layer, the first block in our layers. So Kubernetes networking is essentially at the base two things: the networking stack, which is CNI, for Container Network Interface, and kube-proxy, which we'll get back to a bit later on. And so CNI plugins are responsible for managing the network devices, the IP address management, which is often shortened as IPAM, and the intranode and internode connectivity. So here's a kind of horror story that can happen. You're scaling your nodes or maybe just scaling your pods, and you get a fail to allocate IP address, no available addresses in subnet. This could be when you describe a pod, for example, that is not starting. What is happening here? This is typically a problem with IPAM. And where do IP addresses come from in the context of Kubernetes when assigning IP addresses to pods? It comes from the CNI, so Container Network Interface. The Container Network Interface is the standard that was introduced by CoreOS. It's not specific to Kubernetes. Actually, there's other systems that support CNI, other orchestrators, for example, HashiCorp Nomad supports CNI. And it's a standard interface between the orchestrator and the network implementation. It's responsible typically for IPAM, so assigning one or multiple IP addresses to pods or to containers. It's responsible for routing and the routing logic, and optionally also for security, like network policies. And CNI, in the context of Kubernetes, is called by CRI on each node when pods are created with an add parameter. So CRI will call CNI with add, and when pods are deleted, it will be called with a del parameter. So it looks something like this. Let's say you have a user that posts a new pod to the kube API server. This pod will be scheduled on a node using the kube scheduler. So the kube scheduler will decide to assign this pod to a node. And so it will add to the specification the node name. And then the kubelet running on that node will see the new pod being assigned to the node and is responsible for creating the containers and the whole context to run this workload. So the kubelet will call the CRI, and the CRI will create the network namespace. Talking here about namespace in the context of the kernel, right? Not a Kubernetes namespace. And a pair of network interfaces that we call VETH pair, so virtual Ethernet pairs. And then CRI will call CNI to configure this VETH pair. So typically CNI will assign MAC addresses, will assign IP addresses to the VETH pair. So both the interface that is inside the pod and the interface that corresponds to it to create a bridge on the host side, on the node side. So you see here the two addresses that are linked to each other, each with an IP address, each with a MAC address for the network communication to pass into the pod and out to the node. So CNI is responsible for setting this up, for setting up the routing that will happen there, and also providing IPAM. So if you need to debug CNI, where can you look? You can typically describe the pods. That's where you will see errors. For example, when a pod is not able to start because there is a CNI error. For example, the one I showed before, where there's not enough IP addresses available to assign one. You can look at the kubelet logs as the kubelet on the node will be calling CRI, that will be calling CNI. You will have the errors going up into kubelet logs. And you could look at the CNI logs. So by CNI logs, I mean the CNI plugin. If you're running Cilium, for example, you will have one Cilium pod running on each node. And if you look at the logs of that pod, chances are you'll see details of what is happening, why the pod is not starting. There might be more details of what is going wrong. And know that the configuration is actually on the node. So on each node in your Kubernetes cluster, you have configuration files in etc CNI net.d. And this is what CRI will use to run the different plugins. There might be more than one CNI plugin actually running on a node. They can be cumulative, or they can spread the responsibility as well. So sometimes you'll have one CNI plugin responsible for IPAM and another responsible for routing or for security, for example. And based on this configuration, the CRI will know to call the plugin, and the plugins are located in opt CNI bin on the node. So it typically looks like this. This is an example with Cilium, but it would be similar with other CNI plugins. And here we have the kubelet. The kubelet is watching the kube API server. And when the kubelet needs to create a new pod, it will actually call the CRI, which will call the CNI layer. And the CNI layer will call the CNI plugin, which here is called Cilium CNI. And Cilium CNI, in this case, will communicate with the Cilium agent via socket, local socket, and the Cilium agent will configure the node for routing and assign the IP address, MAC address, and so on. So it's a little bit complicated, but essentially what matters is this part here with the kubelet calling CRI, calling CNI, and the CNI plugin doing whatever needs to be done. Actually, this CNI plugin could be coded in anything you want. Usually it's in Go, but it could be in something else. And then usually the CNI plugin will make a choice of routing mode, which can be configured. Usually you have two choices, either encapsulated or native or direct routing. Encapsulated modes are the easiest. It treats Kubernetes pretty much as a black box where pod-to-pod traffic will be encapsulated between the nodes, so you don't need to care about the configuration of the underlying network. And the traffic that leaves the Kubernetes cluster will typically be source netted. So you will see any traffic coming from the pod and leaving the cluster being netted with the IP address of a node, the node that it left from. There are some extensions that allow to assign specific IP addresses, such as Ingress gateway, that is supported by multiple plugins, but essentially this is the idea. And it requires an encapsulation mechanism. That could be VXLAN, it could be Geneve, it could be IP-IP. So Cilium typically supports VXLAN and Geneve, while Calico supports VXLAN and IP-IP, for example. Native or direct routing means that pods actually will get an IP that is in the underlay, in the network where the nodes are running. This is typically the case when you're running AWS EKS, for example. In EKS, the pods will receive an IP address that is pretty much undistinguishable from the IP addresses of the nodes. So you don't know when you're looking at the IP address if it's a pod or if it's a node in the cluster. And it means the routing will happen pretty much the same way it happens with nodes. Still, the traffic needs to be sent to the proper node in order to be sent to the pod, right? So it means that in this case, the CNI plugin will be responsible not only for assigning the IP address, but also for informing the underlay how to route this IP address. So typically this will use, in the context of AWS, for example, it will use VPC routes, where Cilium, for example, will configure the VPC routing in order to say, in order to reach this IP address, you need to go through this node. On-premise will typically use BGP for this, where you need to have an underlay that is BGP enabled so that you can route traffic to the proper node to access the pod. IPAM is an important topic. So it's the fact of assigning one or multiple IP addresses to the pods, right? It could be IPv4, IPv6, both, sometimes multiple IPv4, multiple IPv6. So again, when a new pod happens, the kubelet will call the CRI will call the CNI plugin, and the CNI plugin will actually return one or multiple MAC addresses and pod IP addresses. There can be different modes, again, depending on the CNI plugin. In the context of Cilium, typically we have two main modes. There's more fine-grained, right? I don't have too much time to get in details. Host scope means that we actually assign one CIDR per node. Usually you take let's take a big CIDR, like 10.0.0/8, 10.0.0/8, so typical, what we used to call class A network, right? And then you slice it into multiple CIDRs, into multiple subnets that you're assigned to nodes, typically a /24 per node. So every node gets a /24, 10.0.1.0 for the first node, 10.0.2.0 for the second node, and so on and so forth. And then the CNI plugin on each node will assign an IP address based on this for the pods that are started on the node. This is the first way. There's pros and cons. The pro is that this is simple. The con is that depending on what you're running on the nodes, if you have big workloads on a node, chances are you will get less pods on it. And so you're kind of fragmenting your subnets for no good, right? You might be having a lot of IP addresses that are assigned to a node and will never be used. So this might not be super efficient. The CRD-backed approach is kind of different. And the way it's different is that it will assign individual IPs to the node. And this is typically what is done in the context of EKS. So here's an example. So like I said, in EKS, the pods are getting IPs from the VPC subnet. And this means that the CNI plugin, in this case Cilium, needs to actually figure out what are the IP addresses that are available to assign from the VPC subnet. So there's an operator here, a Cilium operator, that will talk to the AWS API and retrieve IP addresses that are available to assign in this VPC. And then it will assign these IP addresses to the nodes. So in the nodes, in the CRD representation of the nodes, will have a list of IPs that are available to assign on that node. There are different logics of buffering. You can have multiple IP addresses that are buffered in case you need to start a lot of pods in one go and you don't want to wait for the AWS API to return these IP addresses. But essentially, this is the idea. And so it will allow to have more fine-grained flexibility on which IP addresses are assigned. In the case of EKS, this is what is used by default. It's what we call the ENI mode in EKS. So that's for the basic part, right? The CNI, the base layer. So essentially IPAM, routing. We haven't gone into security, but that's the base layer to allow things to communicate. And then we need services, right? And services, it's not too complicated, but it's still something you need to think of. And essentially, services are these virtual layer 4 load balancer. You can think of a Kubernetes service as a virtual layer 4 load balancer with 3 different layers. It could be cluster IP, node port, or load balancer. So I'm going to go through this. So as I said, the 2 main components in Kubernetes networking are the CNI, allowing for communication between pods and between nodes, and kube-proxy. And kube-proxy is this daemon set, so this pod that is started on every node, and it is responsible for setting up these virtual services, typically using IP tables or IPVS, so some form of net filter implementation, and it provides service discovery with DNS resolutions pointing to virtual IP addresses. Why do we do this? Because we do not want to rely on the IP addresses of the pods that change constantly. You just redeploy a new pod, you just roll out a new version of the application, and you get new IP addresses for your pods. So this is not reliable. So instead, we put a virtual address in front of it, which we call a cluster IP address, and this IP address does not change. It's going to stay the same when you roll out new versions of the application. The way this works is it's essentially, like I said, a layer 4 load balancer that will load balance between the different backends. So when you access this IP address, it will load balance the traffic at layer 4 to the different pods in the backend of this service. We used to saying that this is round robin load balancing. It's not actually round robin load balancing. It's random load balancing. It will send to any pod in the backend randomly. Though, with enough queries, it becomes close enough to round robin, but it's not round robin. So the first layer, the first way of implementing the service is called cluster IP, and this is the default. So type cluster IP, or if you don't specify the type, this is a cluster IP. And the cluster IP is a virtual IP address that is available on every node, and it simply provides this layer 4 load balancing. So when you access the address, it will redirect to one of the pods in the backend. This is simply it. Layer 4 load balancing, random to any of the pods that are ready behind the cluster IP. I could spend some time on this. Actually, I haven't prepared a slide on this, but it's important at this point to understand the difference between liveliness and readiness in Kubernetes. Readiness has an impact on being behind this load balancer. If you want your pod to be behind the load balancer, it needs to be ready, not just alive. One thing that is not used a lot, but it's important to know that it exists in case you see it, is what we call the headless service. And a headless service is a cluster IP type of service where the cluster IP was manually set to none, to the value none. You can actually set the cluster IP manually. It's hardly ever done. And in particular, you can set it to the value none. And what it does is that instead of working as a load balancer, it will only work as a DNS resolution, so as a service discovery feature. and it will return the IP addresses of all the pods that are ready as backends. And then you can choose to access any of these IPs, and you're responsible for making sure that these IPs are up to date, pretty much. So update the list yourself, because again, the IPs can change as you deploy new versions of the pods. Right, so this is hardly ever used. It can be used when you need when your application needs some form of stickiness on the pods, but then you're responsible for keeping it working well. So cluster IP is the base layer, and then on top of this we have node port. So node port is a layer on top of cluster IP, and the way I'm saying this because it implies cluster IP. If you have a type node port, you also have a cluster IP. So this cluster IP can be, again, dynamically assigned, or you can assign it manually. And then when you switch to node port, you'll have additionally a high-level port that is assigned to every node, the same port to every node in the cluster, and you can access this port on every node in the cluster, and it will redirect to the cluster IP. So this simply allows you to expose the service to the outside. So you can access it from the outside by accessing this port that is either pseudo-randomly chosen by Kubernetes, or you can set it yourself as long as it's a high-level port. So that's nice. Now I can access my application from the outside, but I need to access it on that port using a specific node. So what's missing is the last level, which is called service load balancer. So it's a type load balancer. And this is only a specification in Kubernetes to allow for layer 4 north-south connectivity. It's only a specification, as in Kubernetes provides this, but it doesn't implement it. It's up to you to implement it. And usually the cloud provider, so the cloud manager controller, will implement this. So you'll have a controller for AWS, for Azure, for Google, that watches these kinds of services. And when they see it, they will retrieve the node port that was assigned or that was specifically manually put. And they will set up a layer 4 load balancer in front of every node in the cluster and send the traffic to that port on every node in the cluster. Again, probably round robin in this case. I don't know how it's implemented depending on the cloud. You can consider that this is randomly, at least, well spread over the nodes. So now you have one entry point, usually a public external load balancer, that will send the traffic to every node in the cluster, and it gets routed to the cluster IP, which internally will route to each pod that is available and ready. Right, so usually you have this external load balancer. This is typically, it could be an ELB, for example, in AWS. It could be some kind of layer 4 load balancer that sends the traffic to the node port on every node. This is the most common option. If you don't have load balancers that can be programmed this way, some plugins, typically Cilium does this, will allow to actually use a Kubernetes or multiple Kubernetes nodes for this. So what it will do is that it will do the routing internally, and it will assign a public IP address or an externally facing IP address to the service and announce this IP address. This IP address can be announced using BGP, or it can be announced using layer 2 with ARP, for example. So this allows to have a load balancer mechanism in the cluster without having to place a specific load balancer in front, whether an ELB or an F5 or Alteon or whatever. One last thing on Kubernetes services, the implementation. By default, it's implemented using IP tables. You can use IPVS with kube-proxy. There's multiple CNI plugins that allow to actually replace this with an eBPF implementation. This is the case of Cilium and Calico. And this is a matter of scaling and performance. IP tables scales linearly, which means if you multiply the number of pods or services by, let's say, 10, you will multiply by 10 the time it takes to find the right rule or even to start a new pod. With an eBPF logic in the kernel, you can have load balancing that is based on identities, based on labels, and it will scale close to constantly, which means that if you multiply by 10 the number of pods, it won't have an impact on the time it takes to scale, even if you're to route traffic, even if your cluster is thousands of nodes large. A little bit on DNS. Kind of error you can have with DNS, obviously, no such host when resolving a service. DNS is not that complicated in Kubernetes, but there's a few things to know. Typically, there's multiple implementations. One that is commonly used is core DNS, and it runs as a deployment inside typically the kube system namespace. Sometimes the ports are different. Sometimes the implementation is slightly different. Core DNS has its own configuration, its own debug logic and parameters. I don't have time to dive into this, but do go and look at core DNS specifically to understand how it works. Something to keep in mind is that pods have search path in their resolve.conf. And what this means is if you do a ping or a curl on, let's say, Destar, for example, this is the name of my service, it will use the namespace.svc.cluster.local first and check if this can be resolved, and then destar.svc.cluster.local, and then destar.cluster.local, and then eventually at the end, you have the host search, which is taken from the resolve.conf of the host. This is important to keep in mind because it can get to a very big search path, and you might want to tune this in your Kubernetes cluster if you don't want to have too long of a path. You can also tune the efficiency of DNS resolution in your pods by using the ndots configuration. This is really something to look into. Don't have time to expand, but this can save your life if your DNS resolutions are taking a long time. Finally, two domains that are used for DNS resolution in the cluster. This one is very, very known. The name of the service .namespace.svc.cluster.local is typically how you resolve a service using service discovery with kube-proxy or a replacement. And then for pods, you have the same with IP addresses with dashes instead of dots. The namespace.pod.cluster.local, and this is essentially used to facilitate the exchange of certificates for pods. Let's go one layer up and talk about layer 7. So in layer 7, you want to route traffic from the outside, but instead of just doing layer 4 load balancing, where it just randomly goes to a pod, you want something a little bit more advanced. Maybe you want to filter on the path and have multiple services behind one domain name. Maybe you want to filter on headers, or you want to do TLS termination. This is all layer 7 Ingress logic. And typically you'll get errors that are a little bit higher up, and typically like 502 bad gateway, for example, when your Ingress controller doesn't know how to send traffic to the proper backend. In Kubernetes, there is a standard implementation that is called Ingress, the Ingress resource, and this is the standard specification, but not implementation. There is no standard implementation in Kubernetes, just like the load balancer services. So it requires to deploy an Ingress controller that will watch this kind of resources and implement the routes. Could be Nginx, could be traffic, Contour, Cilium does it out of the box as well, and there's others. You might remember, if you're old enough in Kubernetes, that Ingress was a beta resource type for a very long time. And all of a sudden, it became stable. Now, some of you might think, hey, that's because, it's done. We're happy with Ingress. This works. This is great. Actually, it's quite the opposite. What happened is that there was no way to agree on how to implement the features using the specifications. And it got to the point where lots of Ingress controllers use private annotations, like here for Nginx, or even have their own resources, their own CRDs to implement the layer 7 logic. So the reason why Ingress was made stable is to say, okay, we can't agree on this. Let's make it stable and move to something else and learn from the mistakes we've made or the disagreements we've had with the Ingress resource type. And this new project is called Gateway API. You can think of Gateway API as Ingress v2. Ingress v2 as in, this is the new way of doing layer 7 Ingress in Kubernetes. And Gateway API is now stable. You can use it. And there's lots of projects that actually implement it now. And the good news, as far as platform engineering, I used to be quite frustrated as a platform engineer. was Ingress, because people could steal each other's layer 7 routes between namespaces. With Gateway API, this is not possible if you do it well. So the good news is you have a proper separation of concern. Think of it like similar to storage classes in Kubernetes, where the gateway class is provided by the infrastructure, the gateway itself by the cluster operators or platform engineers, and then the developers or users of the cluster can just use routes that are attached to your gateway, but they're not responsible for the domains that are exposed, the ports that are exposed publicly, or the TLS certificates that are available. So it typically looks like, oh my, I went back. Typically looks like this. This is similar to what we had before, where we have a gateway and an HTTP route. So the gateway is the infrastructure side of things, it's the platform engineering side of things, where you will typically decide which port is exposed, which protocol it is, what kind of routes are allowed to be used. Can this be used only from the same namespace or from other namespaces as well? And you could also have like TLS configured there, which domains are allowed, which secrets hold the TLS certificates, and so on and so forth. And once you have this in place, then your users will be able to use HTTP routes and attach them to the gateway, provided it's allowed by the gateway itself. And so they will only specify what kind of logic they want and what kind of backend, what kind of services they want to redirect to. So this is a proper separation. So that's pretty much the future of layer 7 Ingress resources. They could be ton. We could talk about on Gateway API. We could spend a day on it, but I'm constrained in time. So let's talk about internal layer 7, what we call service mesh. Service mesh, everybody wants service mesh. I hope you don't want service mesh just for MTLS, because there's much more to do with service mesh than MTLS. Not everybody agrees on what is service mesh to start with. And typically you'll have the same kind of errors with service mesh as you would have with layer 7 north-south ingress, because this is layer 7 logic, right? Except it's internal to the cluster instead of just north-south. So what is service mesh? Let's just say this is layer 7 infrastructure layer that controls the communication between microservices. It usually provides traffic management, so routing. It provides security usually. It can be network policies, layer 3, layer 4, all the way to layer 7 policies. Mutual authentication in the form of MTLS or something else. Authorization. Observability, layer 7 observability. That can be metrics, Prometheus metrics, logging, traces with OpenTelemetry. And resilience. It can be retries when a service is not working properly, try it several times, timeouts, circuit breaking, stop this service if this other one is not working so that we don't overload the cluster for no reason. And all this ideally in as much a transparent way as possible so that the services don't need to implement this themselves. Your workloads don't need to implement this. This is transparent and provided by the network. So if workload A is trying to reach out workload B and it's not working, you want to implement some form of retry. So workload A is not even aware of this. It will just see the answer, even if it took 3 attempts to get the answer, right? That's the idea. There's lots of ways to implement service mesh. There's lots of implementations. There's Istio, there's Linkerd, tons of things. And in a similar way to north-south load balancing, because there was no existing control plane to implement this logic, there's a lot of different resources provided by lots of different projects. So again, it took a while to get to some kind of standard. The standard that is being built now is called Gamma, and Gamma stands for Gateway API for Mesh Management and Administration. The Gamma project aims to use Gateway API resources, typically HTTP routes, for example, for east-west, so internal layer 7 routing. So that doesn't cover necessarily the security and other needs, but it can cover typically canary, it can cover retries, it can cover lots of different things that would be provided by the specification in Gateway API that are already available for north-south and now can be implemented for east-west. So typically, if I have a pod that reaches out to a service inside the cluster without going out and I want some form of A/B testing with 90% of the traffic going to the first version of the service and 10% to the second version, I can implement this with an HTTP route. I could do this with Gateway API, but instead of using a gateway as a reference, as a parent reference, I will use a service. And this is why it works that way, right? So I can attach it to a service, and as a result, this will be an internal layer 7 routing logic. So this is still a work in progress. More and more service mesh implementations support Gamma. In Cilium, it's coming in 1.16, for example, with support for HTTP routes attached to services. We actually have a lab that shows exactly this in the context of Cilium. I'm going to stop here today, but I just wanted to have a note on security. We could talk about network policies, we could talk about cluster mesh, we could talk about egress gateway, lots of things still, and spend entire days on this. But again, I want to emphasize one thing, which is security. Networking security shouldn't be an option in Kubernetes. I want to insist on one thing when it comes to this. Containers and Kubernetes namespaces are not security features. Just because you have containers running in different Kubernetes namespaces doesn't mean they can't talk to each other. It doesn't mean they can't exchange information. Just because you have two applications running in containers doesn't mean that they don't share resources, or it's not possible to go from one to the other, or to escape from the containers. So again, you need to think about security. I have no time to dive into it, but you need to think about it, both runtime and network security. This could be a whole topic. If you want to learn more about these things, we actually have webinars that are isovalent on the topics of platform. So the power of Cilium for platform operators this month, and simplifying Kubernetes operations with Cilium Ingress and Gateway API in August. And that's my last slide. So I'm happy to take questions now.
Very cool. So we've had quite a few questions flying around the chat, and also quite a few people answering the questions as well and going back and forth. So that is always fun to see. But I think we'll start with the Q&A section. Oh yeah, if you could just go back one slide so people can see your QR codes.
Yes.
And maybe we can leave them up on the screen while we answer
So
questions.
I see some questions in Q&A. What is the best practice to buffer the pod IP addresses or pre-allocate them? So typically the example I was
Let's just one second. I'll just read out the full question, just because people on YouTube and recording won't be able to see it. So I'll just read that one again. So what is the best practice to buffer the pod IP addresses or pre-allocate them if I have a very high pod turnover rate?
Yeah. So if you have typically subnets per nodes, this is not a problem, as long as you don't dry out the subnet for your node. It's available right away. The problem happens more when you have typically a CRD-backed logic where you're getting the IP addresses from an external API, such as AWS in the context of EKS. And you can actually tune the number of IP addresses you will buffer. I think by default, I've seen 8. I don't think it's fixed. I think it depends on the number of CPUs, so that it kind of changes with the size of the machine. I'm not sure. But you can actually tune this number to actually retrieve more IP addresses, at least in the case of Cilium, right? But again, what happens if you get more IP addresses for a node is that you run more chances of actually fragmenting your VPC subnet, right? So it's a balance to find. You don't want to find yourself without VPC IPs in your subnet to assign to nodes or other things. So it's really a balance to find.
Cool. So let's jump into the next one. Is there a way to tweak the random air quotes load balancing method that was mentioned, perhaps doing something like least connections?
That's a great question. The problem is, in order to tweak this, you need to have some form of connection tracking. And usually this connection tracking means you need to identify what's happening inside the layer 7 data and the layer 7 traffic. Because if you have one pod calling another pod, you don't know who is the original caller. There's no trace to identify this. So doing this kind of So least connection would be a thing, yeah. I don't think we do this by default, but typically if you want to go further and actually have some kind of sticky sessions, you need to use layer 7 logic. It's typically possible using Gamma. And there's other things in Cilium, for example, there's an annotation you can add to force using Envoy as a load balancer for like gRPC, for example, which requires specific load balancing algorithms. In Cilium, you can actually tune the load balancing algorithm you want to use. So the default one is similar to kube-proxy, but you can use other algorithms like maglev, for example, an algorithm that was developed by Google as a replacement even for internal load balancing.
Cool. So next one, if we want to leverage container orchestration, but reduce any network overhead in a high throughput 100 gigabyte network for TCP and UDP traffic, is there a setup that provides nearly native performance?
So there's actually a blog post that my colleague Nico, I think, will publish within a few days that will answer exactly this question. The answer is there's different ways to do this, right? So eBPF and Cilium has been used already to reduce the network overhead by bypassing typically some TCP/IP logic in the kernel when two pods are on the same node, for example. There is an option in beta and Cilium for what we call big TCP as well. And so big TCP is the possibility of having jumbo packets so that you have less packets that are sent, right? So this also reduces the latency. And finally, what is coming and is super exciting is a new layer in the kernel that is called Netkit that was merged in kernel. I think it's 6.7, something like this. I'm not sure. It's in the 6th branch. And Cilium is the first CNI to make use of this Netkit API, and it allows to have host native performance. So now all the tests we've done, you have the same latency and same throughput as the host itself. So there's a blog post that's coming on this. It's super exciting, actually.
I think you could share that blog post in the platform engineering Slack.
Yeah,
I
as
think
soon as it's published. I'm not sure it's
that would
published yet.
be helpful for
I've
people.
read it, but I don't think it's published.
And for people who don't know yet, if you do want to, have continue the conversation, ask more questions, or see more resources, you can join the platform engineering Slack. There's always a lot of good stuff going on in there. So over to the next question. Is there any way to ensure that some nodes are always in running state using Carpenter Autoscaler for critical pods that need to be scheduled quickly?
That's a good question. I think I don't have a quick answer to this. I'm guessing what you want is to make sure that you have pods, that nodes that are ready with daemon sets already running, but nothing else, right? I'm guessing this is a question. I'm not really sure. I think if you start the nodes and then you cordon them immediately, you will start the daemon sets and then prevent anything else. I'm not sure about this. Yeah.
So then the next question, can Cilium support gateway API management? If yes, then how is it different from Kong?
I'm not sure what you mean by gateway API management, or do you mean API gateway management? Because this is a common mix-up, and it's fully understandable, right? Between gateway API and API gateway. Gateway API is a standard from the Kubernetes project to implement layer 7 routing, whereas API gateway is usually some kind of system to manage multiple APIs in one way. And typically projects like Kong provide this kind of solution. Cilium doesn't. So Gateway API is just the YAML resources in Kubernetes that allow to program layer 7 routing in Kubernetes.
And another one, any tips for debugging the networking setup in Kubernetes? Example, after setup of Ingress, service pod, etc., somehow there are not responses coming back.
So my tip, I'm obviously biased when using Cilium, is that Cilium comes with a tool that is called Hubble. And Hubble provides a lot of visibility from layer 3 all the way to layer 7, depending on how you configure it. Typically, if you want layer 7, you will deploy network policies at layer 7 that will send the traffic through Envoy and get the metrics from there. And Hubble will provide a service map. It will provide metrics. It will provide lots of things to debug lots of things, right? So we have dashboards in Grafana, for example, for everything related to DNS, related to TCP, to UDP, and so on. So that definitely helps a lot.
Let's see if we've got some more here in the chat. A few more have popped into the Q&A. So what's the flow of network communication when we map external DNS to ingress controller, load balancer, external IP?
It depends. It depends on how it's implemented, right? An ingress controller essentially can run in a different way. It can be simply a deployment, a pod that is running in your cluster and is just a standard pod. In the case of Cilium, it could also be a specific identity that is managed by Cilium in a special way. And usually you'll have a load balancer. Again, the load balancer can be somewhere in front, provided by the cloud provider, or it could be in the cluster, like in the case that I explained with Cilium and LBI PAM. So when you use external DNS, essentially external DNS, what it does is that it will take the public DNS, the external DNS, the external IP, sorry, that is assigned to the service, and it will create the DNS entry to redirect to it. The way it's routed afterwards, again, totally depends on how you're implementing load balancers with an external load balancer or within the cluster with BGP or something else, and how you're implementing the ingress controller itself, whether it's managed by the CNI, managed by the service mesh, or a pod on its own. That really depends.
So I see a few people asking about the recording. So the recording will be available on the Platform Engineering YouTube channel. So we're actually streaming live there now at the same time, and that recording will be there. So you can see that. And we'll be sending out slides to everyone who's attended. So you can see the slides and stuff like that. So we've got a bunch new questions that just popped in.
Yeah, the more we answer, the more
the more we answer, the more. So let's dive into this one. Can we set up an Istio Ingress gateway with an AWS NLB, perform TLS termination at the Ingress gateway level, and use Cert Manager for managing the TLS certificates? So I look forward to you unpacking that one.
This is a big question. Can we set up an Istio? So I'm not an Istio expert by any means, so I'll say this to start with. Can we set up an Istio Ingress gateway with an AWS NLB, perform TLS termination at Ingress gateway level, and use Cert Manager for managing the TLS certificate? Yeah, that seems totally plausible. Yeah, like it wouldn't be just Istio, but just any, I would say any layer 7 ingress, whether using the ingress resource or gateway API or something similar, normally can do TLS termination based on certificates that are stored as secrets in the cluster. And this TLS secrets can be provided by Cert Manager based on annotations. The question though, and I'm pretty sure that's what I don't know, is that, yeah, Cert Manager needs to be able to parse the resource, typically the ingress or gateway resource, and extract the secret name and the domain names that are required and make the request to generate the certificate and store it in a secret. That might be the part where I don't know if it supports ingress gateways. I don't know about this. I would suppose, because I mean, Istio is kind of a standard. So
I think what could be interesting there for you as well would be to share that question in the Platform Engineering Slack, because I think that would be one for a back and forth, maybe if you have
surely there'll be an Istio expert there.
Yeah, there'll definitely be someone who'll be like, this is my moment. And you'll get a fantastic answer and you can go back and forth on that. I think that will be helpful. So the next question is, any recommendation on how to get started and perhaps dive deep with Cilium and Kubernetes networking in general?
Oh, you're tapping right into my favorite topic. So I'll share the screen again for a few seconds. One thing that I do a lot is I create labs. This is one of the main parts of my job. So we have tons of labs on isovillain.com. There's like 30 labs that you can take. They're all free. There's even like a fun map where you can explore the labs. And we have regular workshops when we run the labs with you if you want to run them with us, but you can take them anytime. And this cover, I wouldn't say everything. We still have quite a few to do, but from basics to network policies to layer 7 routing to pretty much most of the topics. And if there's a topic that you would like to see, let me know because I'm always happy to hear about what users want to see.
Very cool. Yeah, maybe there needs to be another webinar at some point as well. There's just so much that that needs covering. We've got a question here just on that. Can you make another webinar about runtime and security?
I'm happy to. Personally, I don't know about you.
Yeah, there's been a lot of demand, I think, so we'll have to figure something out for that. Another question from William. Talking Hubble and Cilium, what's the difference between Cilium Monitor and Hubble Observe?
That's a good question. Cilium Monitor is low-level information. Pretty much you'll get more or less the same information, except Cilium Monitor is very raw, hard to understand kind of, and it's only on node per node, right? So you get on the node and you see Cilium Monitor. Hubble allows to have a more understandable format. It uses JSON flows, and it can aggregate the JSON flows from all the nodes in the cluster, so you can see everything from all the traffic on all the nodes and then filter them using flags. So Hubble is more usable. Cilium Monitor can be more useful for deep dive debugging.
Interesting. So another question, is it feasible to do Canary and layer 7 without a service mesh? Maybe with Cilium?
So in theory, yes, not just in theory, but gateway API, HTTP routes allow to have weights. So you can set a weight to multiple services and say, you know, like 80% of the traffic goes to one service, 20% goes to another service. What's missing is the controller, right? So if you have a controller that will change the values for your HTTP route, which now you can use either for north-south with a gateway or for east-west with a service using Gamma, then you can have a canary approach. So you just need the controller to change the values as you roll out.
Very cool. So if there's any more questions coming in the chat, we've still got 5 minutes, so feel free to ask away. I know, oh, they're already popping in. We can just quickly take this one from Ricardo. I think you could Google that as well, but while we're here, we can jump in. What's the pricing model of Cilium?
Joker, I'm not answering this. I'm in marketing, not sales. It's at this point it's per node, and it's evolving, but I don't have details.
That's a mystery for you to go solve, Ricardo. We're talking about Kubernetes, and that's a different question. So another one, off topic, can you tell us some cool VS Code themes that you're using?
Like personally, I'm not using themes. The one plugin that I couldn't live with probably is a Vim plugin, so that I can use VS Code with Vim bindings. Besides this, I haven't looked into themes. I switched to VS Code very recently because I switched from Linux to Mac when you might know Isovalent was acquired by Cisco, so I had to change my machine. So I got a Mac for a change to make videos and so on. And yeah, that's when I got started with VS Code. So I haven't been diving too much into themes yet.
So in your next webinar on security, then we can dive into your VS Code themes. We'll give you
Okay.
more time.
That gives me time to look into it. I'll have some vacation in the meanwhile.
Oh, another one has just come in. Is there any recommendation how to easily integrate Cilium with Grafana or Datadog for observability purposes?
So lots of Cilium components provide metrics. You have Prometheus metrics provided by Cilium agents, by the Cilium operator, by Envoy, by Hubble Relay. And there are dashboards that already exist. There's a set of dashboards available in the Isovalent organization on the Grafana website. As for Datadog, you can try to mimic the dashboards that exist. I'm not sure there's some out of the box. We also obviously get regular requests for Splunk and Elasticsearch. Yeah, so generally speaking, Grafana is the easiest because there's some dashboards that are public for sure.
Very interesting. I think that might be everything. If
Right.
there's no other questions coming in, now is your last chance to, oh, here we go. What overlay means in networking?
Well, good question. Uh, I'm so I'm not a networking engineer, so if I say something stupid, someone correct me, or at least remember I'm not a networking engineer. The idea of an overlay is that it's a layer that is on top of another layer, right? So in the context of Kubernetes, when we talk about overlay routing, it means we have a network fabric for typically the nodes, right? Where we have IP addresses assigned to the nodes and routing logic was maybe gateways for that network. And then instead of routing the pods on the same network, we're creating an overlay network where the traffic will be encapsulated, and we can use whichever typically layer 3 that we want on that overlay because the IP addresses will actually not appear. We'll add some prefixes to the packets so that they get routed to the nodes properly. So that if pod A wants to talk to pod B and they have like an IP address in 192.168, for example, and this is not a native IP address to the underlay, to the network where the nodes are provisioned, then the packets that are sent, the node that sends the packet knows which node is hosting the second pod, and it will send the traffic to that node with the IP address of the node containing the packet that needs to be sent to the pod. So the pod will think it's direct communication, but it was actually encapsulated. You can think of, yeah, kind of like a VPN is a form of overlay that is encrypted, right? Except it doesn't need to be encrypted. In the case of Cilium, you can actually encrypt the overlay network, but you don't have to, right? I don't know if that made sense.
Well, I think people in the chat are very happy with these answers. So thank you so much, everyone, for joining, and thank you, Raphael. I think this was really fun for everyone. We covered a lot of ground.
Yes,
So just a
that's the
quick
challenge.
reminder.
There's a lot of ground to cover.
A lot of ground to cover, definitely, but I think we did a great job. And thank you so much, everyone, for your questions and for participating. And just a reminder that you'll be able to find the recording of this session on the Platform Engineering YouTube channel, and you can find more conversations, discussions, or if you want to reach out with Raphael or myself directly, you can reach out to us on the Platform Engineering Slack channel. And of course, there's endless sea of more content like this coming from Raphael and through the Platform Engineering blog. So thank you so much, everyone, for joining. And thank you again, Raphael. And have a great rest of your day, wherever you are.
Take care.
Bye.